the data density of a single photon. A single photon of filtered starlight reveals more about an alien world than a million-pixel photograph. While the public expects high-definition images of continents and oceans, the European Space Agency is betting the next decade of discovery on smell. This is not about taking pictures, but about breaking light into a chemical barcode that reveals what a planet is breathing. The failure of direct visual imaging. Seeing an Earth-sized planet next to its host star is like trying to spot a firefly hovering inches away from a stadium floodlight located 5 miles away. The contrast ratio is the enemy of engineering. If we rely on sight, we spend billions on star shades and coronagraphs just to see a single pale dot. This pursuit of a visual image is a strategic trap that yields high-cost, low-information results. We do not need to see the blue of an ocean to know it is there. We only need to catch the light that filters through the atmosphere as the planet passes in front of its sun. This transit spectroscopy turns the entire planet into a filter, and the resulting signal tells us exactly which molecules are present without ever seeing the surface. Building the dedicated chemical sniffer. With the flight model integration now underway as of May 2026, Ariel represents a fundamental pivot in mission architecture. Unlike the James Webb Space Telescope, which is a general-purpose tool, Ariel is a dedicated specialist designed for one task: sniffing. Its 1.1-meter telescope is small, but its photometric stability is unrivaled. The mission successfully passed its structural and thermal tests last month, proving the spacecraft can maintain the extreme cryogenic temperatures needed to detect infrared signals from distant gases. By focusing exclusively on hot exoplanets, Ariel ignores the visual noise of the galaxy to find water vapor, carbon dioxide, and methane. It is a mass-produced approach to science. Instead of spending months staring at one interesting rock, Ariel will survey 1,000 planets. This scale moves us from anecdotal evidence of life to a statistically significant census of planetary chemistry across our sector of the Milky Way. The move toward planetary population studies. We are exiting the era of the planetary hunter and entering the era of the planetary chemist. Ariel does not care about finding a second Earth. It cares about understanding the chemistry of the entire neighborhood. This massive dataset will finally explain why some solar systems look like ours while others are chaotic and toxic. The real implication. The shift from sight to smell marks the end of our obsession with finding a visual twin of Earth and the beginning of a cold, analytical search for biological signatures. By prioritizing transit spectroscopy and photometric stability over direct imaging, we are admitting that the human eye is the wrong tool for this job. Ariel's census of 1,000 atmospheres will prove that habitability is a chemical spectrum, not a binary choice between Earth-like or dead. This mission transforms exoplanet science into a big data industry, where the signal under the noise is no longer a blurry image, but a verified, atmospheric composition. For developers and strategists in the space sector, this means the future of discovery is in specialized sensors and autonomous data processing, not larger mirrors. Watch for the first batch of chemical surveys in late 2029. They will likely reveal that water is common, but stable atmospheres are the true rarity in our galaxy. Subscribe for more.